Let us see how a high pass filter will behave if a step input is applied to it. So here the Vi, the input voltage Vi, is a step signal of amplitude V. Let capital V be the amplitude of the step signal and Vi be the input applied, and we are supposed to find what is V naught. For this, we may need the support of, we will use Laplace transform. Okay, so we will use the concept of Laplace transform to find the output or the response of this high pass filter to a step input. So let us use Laplace transform for this. So what I'm doing is I'm converting this figure, this circuit diagram into the Laplace domain. So what I will do is the circuit remains same, but the component values will be changing. So instead of here it is Vi of t, in the Laplace domain I will write it as Vi of s. V naught of t output in the time domain, in the Laplace domain, is denoted as V naught of s. Let V naught of s be this. Okay, R is same, R in the Laplace domain, and C becomes 1 by SC in the Laplace domain. Okay, and I of t, the current I of t, is denoted as I of s. So I have converted all the components here to the Laplace domain. Okay, so now we know that Vi of s is actually, this is the Laplace domain, Laplace transform of a step input. The input is step input, right? So what is your Laplace transform of u of t? Laplace transform of u of t can be written as 1 by s, right? So this is equal to V. See here this is 1 by s, right? So here the magnitude is V. So this is equal to V by s. Okay, if it is of unit magnitude, then it is 1 by s. Since the magnitude of the input is step is V here, this is equal to V by s. Okay, so this is V by s. Now let us write the KVL here, Kirchhoff's voltage law expression. So V by s can be written as V by s is equal to 1 by SC into I of s, 1 by SC into I of s, that corresponds to the capacitor part, plus R into I of s, R into I of s. Okay, so this can be rewritten as, this is equal to I of s into R plus 1 by SC. So I of s into R plus 1 by SC. Okay, so let that be equation number 1. So this is Vi of s. Vi of s. This is expression for Vi of s. Okay, so let it be Vi of s. So we'll start with input. So Vi of s is equal to 1 by SC into I of s plus R into I of s. I will take I of s outside, R plus 1 by SC. Similarly, what is V naught of s? Output V naught of s. V naught of s is equal to R into 1 by SC. Correct? V naught is actually the voltage drop across R. So R into I of SC. So let that be equation number 2. Now let us take the ratio, divide equation number 1 by equation number 2. So divide 2 by 1. So you will get equation 2 divided by 1. You will get V naught of s divided by Vi of s is equal to R into I of s divided by R plus 1 by SC into I of s. So R into I of s divided by R plus 1 by SC into I of s. So here two terms will cancel, I of s and I of s, these numerator, this term will, I of s term will cancel. So this can be written as R divided by R plus 1 by SC. Or you take the the LCM of the denominator. This can be written as V naught of s divided by Vi of s can be written as R divided by SRC plus 1 divided by SC, and this will come to the numerator. So this becomes SRC divided by 1 plus SRC. Okay, so let this be equation number 3. Okay, so V naught by Vs is equal to R SRC divided by 1 plus SRC. Now, V naught of S by Vi of S is equal to SRC divided by 1 plus SRC. We obtained this as equation number 3. And from this, we already know that what is Vi of S? Vi of S is equal to V by S, correct? We have seen here. Vi of S is equal to V by S. Why? Because it is a step function. So it is V by S. So I can write it as V naught of S. This can be written as V naught of S divided by Vi of S. What is Vi of S? It is V by S is equal to SRC divided by 1 plus SRC. And here I will bring this denominator V by S to the other side. So this implies V naught of S is equal to V by S into SRC divided by 1 plus SRC. Here again the S term will cancel. So this S and this S will cancel, and this can be written as V into RC divided by 1 plus SRC. Okay, so V naught, we have now an expression for V naught of S. This is equal to V naught of S. Okay, this is the expression for V naught of S. Okay, now if you take, just take the inverse Laplace transform of V naught S, take inverse Laplace transform of V naught of S, we will get what? We will get V naught of T. This is what we want. This is actually the response to step input. This is actually we want. Okay. Now, to take the inverse Laplace transform, the denominator here, right? So the denominator of V naught of S must be of the form, say S plus something, right? S plus some constant. Okay, so the denominator 1 plus SRC must be of the form S plus something. Okay, in this form. If this is in the form S plus something, then we will be able to find the inverse Laplace transform quickly. So let us convert it to that form. It's very simple. What we have V naught of S is equal to V into RC divided by 1 plus SRC. So just take RC outside. So this is equal to V into RC divided by RC into S plus 1 by RC. Correct? So this is now of the form S plus we have obtained, right? And RC will cancel here. So this RC and RC will cancel. And what we will get? Once if you cancel, what I am getting is this is equal to V divided by S plus 1 by RC. Correct? So V naught of S is equal to, this is V naught of S. Okay, so this is now the expression for V naught of S, and we are supposed to take the inverse Laplace transform. Take inverse Laplace transform of this expression. Very simple. So let's just take inverse Laplace transform of this expression. You will get the V naught of T expression. Okay, so let me rewrite it again. What is V naught of S? V naught of S is equal to V divided by S plus 1 by RC. V divided by S plus 1 by RC. So take the inverse Laplace transform. Take the inverse Laplace transform. I will get V naught of T. V naught of T is equal to V into, what is the inverse Laplace transform of e raised to minus a 1? see 1 by s plus a. I hope you remember inverse Laplace transform of 1 by s plus a is e raised to minus at, correct? E raised to minus at. So what I will get is, if I take the inverse Laplace transform of 1 by s plus a, this is e raised to minus at. So coming here, v is constant, so v into, if I take inverse Laplace transform, instead of a, it is 1 by rc. So we will get e raised to minus t by rc. So this is very, very, very important. This is the response v naught that I get if I apply a step input. So this is the response. This is the response of high pass filter to a step input. If I apply a step input, this is what I am getting at the output. Okay, so if I plot this, what I will get? If I plot this v e raised to minus t by rc, this is exponentially decaying. This is actually an exponentially decaying function. Okay, so if I plot this v0 of t, v naught of t with respect to t, what I am getting is an exponentially decaying function. So this is an exponentially decaying function. It decays like this. And what is its magnitude? This is v. Why? Because v is a maximum value, right? So v at t is equal to 0. What happens at t is equal to 0? Here, at t is equal to 0 means e raised to 0 becomes 1. So v0 of t is equal to v. So v0 of t is at t is equal to 0, the amplitude is v, and it decreases exponentially. And this is denoted by this is v e raised to minus t divided by rc. Okay, so this is how a high pass filter, of resistor value R, capacitor value C will respond, right? Will respond if I apply a step input. So if I apply a step input of magnitude of amplitude V, this is a step input. If applied to as Vi to the low pass filter, high pass filter, then the output V naught is the output. Okay, so V naught is obtained like this. So if I apply a step function of amplitude V, the output, the response of the high pass filter will be an exponentially decaying function. Okay, you will get an exponentially decaying output, which is of the form v e raised to minus t by rc. So we have seen that if a step function of amplitude v is applied to a high pass filter, the output of the high pass filter decays exponentially, and it is denoted by the expression v naught is equal to v naught of t is equal to v e raised to minus t by rc. We have seen that we have derived this. Okay, so v e raised to minus t by rc. That means the output of the high pass filter decays exponentially. This is how a high pass filter responds to a step input applied to the input of the high pass filter. Step signal applied to the input of the high pass filter. Now, so we have seen that v naught of t is equal to v e raised to minus t by rc. Let me write it again. V naught is equal to, or v naught of t is equal to v e raised to minus t divided by rc. Now, what happens? Here we have, please note the term rc. We have a term here rc. So here is a term, this term rc. So this rc is called the time constant. The RC is called the time constant. So let us see the significance of this time constant. So RC is called the time constant. So now let us see different cases of this one by one. Suppose if t is equal to 0, what happens if t is equal to 0? What is V0? V0 is equal to V e raised to 0. That is equal to V. So that is case 1. Case 1. If t is equal to 0. Now, case 2, if t is equal to RC. RC means one time constant. RC means one time constant, right? So if t is equal to RC time, so one time constant. Okay. So what happens if t is equal to one time constant? If t is equal to one time constant, V naught is equal to V e raised to minus t. What is t? RC. Minus RC by RC. Okay. So this becomes V into e raised to minus 1. That is equal to 1 by e times V. Okay. What is this 1 by e times V? So that is equal to 0.367 into V. Okay. So 1 by e times V is equal to 0.367 V. Okay. So I will write here in one time constant duration, voltage output, basically output reduces from V to 0.367 V. Agreed? In one time constant, output reduces from V to 0.367 V. That means approximately 63% decay, right? Approximately 60, yeah, it is approximately to 0.37, right? 0.367 is approximately equal to 0.37. So 0.37 means it reduces 63%. So approximately 63% decay happened in one time constant. Okay, that happened in one time constant. Approximately 63% decay in one time constant. So initially it was V. Now after one time constant, it reduces to 0.367, 0.37, right? So that is equal to approximately 63% decay. Now again check what happens if let case 3. The case 3, if t is equal to 2 RC, that means 2 times time constant. If t is equal to 2 RC, what happens to V naught? V naught is equal to V e raised to minus 2 RC. Instead of t, minus 2 RC divided by RC. That is equal to V e raised to minus 2. That is equal to 1 by E square into V. 1 by E square into V. What is that? 1 by E square. You compute, you will see that it is 0.135 V. 0.135 V, correct? So that means the conclusion is that in 2 time constant duration, output reduces to 0.135 V. 0.135 V is, what is this 0.135 V? 0.135 V is approximately 87% decay. 0.13, right? 0.13 is approximately 87% decay. So in 2 time constant, output reduces almost 87%. Output reduces to 87% of the initial value. Output reduces to 87% of the initial value. Okay. Now let us see the next case. Let us see at what happens at 3 time constant. So let us see the next case. If t is equal to 3 RC, what happens? 3 RC. 3 RC means 3 times time constant. Then that implies V naught is equal to V e raised to minus 3 RC divided by RC. That is equal to V e raised to minus 3. That is equal to 1 by E cube into V. That is equal to approximately, if you solve this, you will see that this is equal to 0.049 V. Correct? So in 3 time constant, output reduces to 0.049 V. That is approximately 0.05, right? 0.05. That means approximately 95% decay. So in 3 time constant duration, output reduces to 0.05 not 49. That means 95% decay will happen in 3 time constant. Okay. Then next case, let's say the fifth case, if t is equal to 4RC, that means 4 time constant. What happens in 4 time constant? V naught is equal to V e raised to minus 4RC by RC, that is equal to V e raised to minus 4, that is equal to 1 by e raised to 4 times V. What is 1 by e raised to 4 times V? It is 0.018 V. That means almost 0.2, approximately 0.02, sorry, 0.02 V. That means the conclusion is that in 4 time constant time, in 4 time constant duration, output reduces to 0.02. 0.02 means 98% of initial value. Okay, reduces to 98% of initial value. Correct? Now, and finally one more case 6. If t is equal to 5 time constant, 5RC. 5RC means 5 times time constant. What happens to V naught? This implies V naught is equal to V raised to minus 5RC by RC. That is equal to 1 by e raised to 5 times V. 1 by e raised to 5 times V. Okay, so that is equal to 0.007 B. That means almost greater than 99% decay, almost zero. So that means in 5 time constant duration, output reduces to greater than 99% of initial value. Okay, so that means output almost reduces to zero. Okay, so let me again redraw it here and explain what happens. What is the impact of, or what exactly a time constant means. Okay, so this is t, this is V naught. The response to a step function is nothing but exponentially decaying. Now what happens is that initially at t is equal to 0, it is V. We have seen here at t is equal to 0, V. Now what happens if t is equal to RC, 1 time constant? It reduces to 0.367. So it reduces to, in 1 time constant, this is 1 time constant. So this comes to almost, say, 0.367 V. That means 63% reduction. 63% reduction. Now, what happens in 2 time constant? If t is equal to 2RC, it becomes 0.135. So again in 2RC, time, 2 time constant time, this comes to almost 0.135 V. So that means almost like 87% reduction. 87% reduction will happen in 2 time constant. Now what happens in 3 time constant? In 3 time constant, again here, in 3 time constant, we have seen here in 3 time constant, output reduces to 0.05, 0.49, correct? So this becomes 0.049 volt. That means That means it reduces to 95% reduction. It reduces to 95% of the initial value. Okay, it reduces 95% of the initial value will be reduced. Now, what happens in 4 time constant? In 4 time constant, we have seen here in 4 time constant, in 4 RC time, approximately 0.02 volt, 0.02, correct? So it goes to 0.02. So the scales may be different here. So 0.02 V. So that is almost 98% reduction. And in 5 time constant, basically in 5 time constant time, so in 5 TC, almost 0, right? Greater than 99% reduction. Okay, so that means we conclude that. So what is our conclusion? We can conclude, we can give some conclusion or analysis based on this. Our conclusion is that, in 5 RC time or in 5 time constant time, in 5 RC time or 5 RC duration or 5 time constant duration, in 5 time constant duration, the output has reached approximately 0. The output reached approximately 0. Okay, so in 5 time constant, final value will be reached. So initial value is V. In 5 time constant duration, final value is reached. Okay, so final value is reached in 5 time constant duration. Okay, so this is how a high pass filter responds to a step function applied to the input.